Hello and welcome to our Geomagic Design X overview. We're going to talk a little bit about the software capabilities, and then we're going to go over some specific software applications and workflows a little bit later in this series. So to start with, we're going to talk a little bit about where Geomagic Design X fits in the Geomagic software product line. Design X is in the digitized section of the steps that we've outlined here, and it's also under the Geomagic brand of software. That means it's in the scanning and modeling softwares that G3D Systems has. We also have some CAM and tool and die software under the Cimatron and GibbsCAM portfolio. So DesignX is in the digitized section, which means it connects directly to scanners as well as accepts other scan-based files. And it takes that information and converts it into something a little more usable. It could be a closed watertight solid, or it could be a closed watertight mesh. If we want to go directly to 3D printing or to a CAD environment, we have the capabilities in the software. So, where did Geomagic come from? So in the 3D Systems product line, we have a number of different software that have been consolidated from a number of different companies. Starting in around 2011, we started with acquiring a CAD software, and today we've boiled these down into a number of different software. So the product we're going to talk about today is Geomagic Design X. This has been consolidated from two major companies, Geomagic and RapidForm, and the products XOR, or Redesign, Geomagic Studio, Geomagic Design Direct, and a number of different plugin software have been compiled into Geomagic Design X. Design X shares some of the capabilities and functions of each of these softwares, but we've decided to move forward and develop this software to better suit your needs as well as the resources we have as a company. So specifically, where does Design X fit into the overall manufacturing workflow? For the most part, it starts towards the beginning, so sometimes you can integrate Design X to a later step in the process, but for most users, we're in the first stages of the workflow. This means this is a very small portion of the workflow. So Design X has been developed and created so you speed up the front half so you can go to manufacturing faster. So in Design X, we have a number of different workflows and things we can do to get there in the quickest way possible. We can go through a complete parametric feature-based modeling workflow. So we have as is design model, or we can go very quickly into a watertight solid for direct 3D printing. So what exactly is Design X? Design X is in the simplest sense, a reverse engineering software. That means we can take an object and create the CAD model or the designed model that was used to manufacture that object. And this is very common for people who either never had a CAD model of a part, the CAD model was lost, or they're just trying to generate a new CAD model from a part that they've just prototyped or manufactured. This could be because of a number of reasons. They found a part or the part was handmade and would need a CAD object. There's not that many softwares that are able to do this, and Design X is one of the best. It can create a feature-based parametric model of the part. It has a full CAD toolset that interacts directly with the scan data to generate a full parametric model very quickly. And then we have the ability to take that parametric model and history tree of the model and then bring that into a native CAD package that we're used to working with. This means we have the ability to use the assemblies or drawing or other simulation tools in a native CAD package with a lightweight CAD, and we don't have to worry about dealing with the scan model. Design X also has the full mesh capability. We've developed all the mesh tools, and then we've integrated that with the CAD tools to show a complete set of tools to encompass all steps in the process. Not only this, we've developed a very high-performing platform that integrates all these tools into one easy-to-use software. When we talk about reverse engineering, there's a lot of different types of things that we talk about. A lot of it has to do with scan-based terms like meshes and point clouds and polygons. And we also use CAD terms, so we have to be familiar with all kinds of things. And here are some of the definitions of commonly used terms that we use when we're talking about reverse engineering and modeling. So to start with, we're going to talk a little bit about two basic workflows in Design X, and we're going to go through them. We have the ideal feature-based modeling, generating a parametric model of the part. And you can kind of see that on the left-hand side of the screen. We have an assembly of pipes in a building. We want to get the exact diameters or paths of these pipes. The same thing we can do on the ideal surface modeling, and that's when we have more organic shapes that we don't want to or don't have the capabilities of modeling parametrically, and we want to capture that surface very exact. So example of a scan of a hand, we need to know the exact form of someone's hand to do any modeling down the line very precisely. And then at the top of your screen, we have an example of a side-by-side comparison of the two. On the left, we have a feature-based model, so we have nice flat surfaces, nice consistent cylinders. On the right-hand side, we have a number of patches that make up the face of this object. So with that being said, we're going to hop right into the software. So here we are in Design X. We have a scan of our gas valve here right in front of us. If we zoom in here, we can take a look at the triangles themselves. So the scanner picked up all of these vertices of our triangles, and we've used the tools in Design X to first mesh them together into this STL or mesh type file format. And we've also gone through and scanned the top and the bottom half and brought them together. So now we have a complete closed object of our scan, and we're ready to start our modeling workflow. So something else we've done ahead of time here is we've applied a region group to our part. What this means is we've taken all these scan points and we've applied basic primitive shapes to these areas. So the software can go through and categorize the area by curvature and then identify a base primitive to that area. So if I come over here and hover over the opening of this valve, the software identifies this as a plane. You can see underneath my cursor that the software is determining that this shape is a plane. So the software also can do the same with curved shapes. So we have cylinders. We also can do spheres and other torus and other basic primitives that are solid type formats. So this is still a scan object, and we're using these tools to speed up the modeling workflows to give us an indication of what this shape could be as a CAD feature. We encounter more complex shapes like lofts and sweeps and other things like that. We determine those to be freeform objects, so we can hover over this filler here. And the software doesn't identify this as a basic primitive shape, but we still have this as a selection area or selection set that we can go through and apply certain modeling tools to these areas. So what we're going to do is we're going to model the bottom skirt of this valve, and we're going to walk through that process right now. So in Design X, we have a tool that we use most of the time, and we call that a 2D mesh sketch. And what this does, it works like a regular 2D sketch in CAD, but it interacts directly with the scan objects very quickly. So I'm going to go ahead and use my right-click contextual menu here to right-click on this top plane and click on my 2D mesh sketch setup button. So what this does is it brings me into a setup stage where I can go and set up this 2D sketch. So in my screen, I have this solid teal line, which is where the base plane that I started with intersects the mesh object that I've scanned in. So I'm going to hide my region groups to better visualize this. And what I can see is that this teal line isn't solid or isn't going all the way around the cross-section of where I started. This is because the part itself is a little bit worn. This gives me an indication that this part isn't perfect, and I might need to make some modeling calls to actually model this the way it was originally intended, or I can use the tools to extract the as-is geometry and still get a CAD parametric model, but using the dimensions from the modeled, the physical part. So in the tool set here, I have two arrows here. So I have a larger arrow in the center of my part, and I have a smaller arrow on the right-hand side of my part. And the center arrow here, this is an offset value. So I can click and drag this offset value, and it will change where the 2D mesh sketch setup interacts with my scan object. And as I move this across the part, the solid teal line updates to whatever the offset value intersects with the part. I get that shape. And then back on my base plane, I get a dotted line, which is where my reference will start on my base plane. So the the second arrow here turns the 2D cross-section I have into a 3D box. So this is handy if I have an area where it's very challenging for me to scan, or I just need additional reference for my setup. I can get this information and project it back to my base plane. So for this part of the modeling process, I'm just looking for the cross-section at the bottom. So I just need to offset my plane just a little bit so I intersect the entire part of the base, and I can go into my sketch. So all the dialog options here can be edited as a numerical value instead of using the mouse to drag these offset values around. Going into our 2D sketch here, I'm going to hide our mesh. The solid teal line, or the dotted teal line, has turned into these pink reference polylines. So here at the top, we have all of our regular 2D sketch tools, and these behave just like regular sketch tools. I can come here and start drawing lines. This will automatically apply some constraints for me, and this is very handy and very familiar to people who are used to dealing with CAD. But the tools in Design X lend themselves very easy to people who aren't as familiar with CAD. So if I click back on my line tool here, I can see that some of the solid pink lines in my polyline reference have turned into a dotted line instead of a solid line. This means the software is going through and identifying the curvature of these lines and trying to classify them as straight lines or not. So just like we do an overview of the part in 3D and apply regions to the surface, we're going and doing the same thing, but on this 2D cross-section. So I can see the center hole of my valve here isn't a straight line, so the software has identified this as a dotted line, whereas the sides of my part here are straight, so they turn solid. So if I come over here and highlight the side of the part, the software is going to try to fit a straight line to it. So I can just click and it'll apply this blue CAD line to this pink polyline. So I can go in and easily model the outside of my part. Now if I get to an area like such as the bottom, where the straight line doesn't go all the way across, what I can do is I can click on the part that the software is identifying as straight, and then I can use a manual selection to select additional parts of this polyline to fit to my straight line. So I can come over here and box select, and then it will extend its fit to across this little part of the valve. So this is very handy when we're encountering shapes that are not perfect or maybe are a little bit worn, and we still need to fit this kind of geometry to it. So I can select any sort of geometry, and it'll show me that it's highlighted teal here, and it will fit whatever CAD or sketch geometry I'm using to my selection of my pink polyline. So we're going to come in here and just use some of the other CAD tools to finish up modeling this part. So some of the tools here are going to be familiar to certain people who use certain CAD packages. Because we have the ability to go to any CAD package after we're done here, we're going to have an overlap of all of those tools and functionality. So we'll come out here and say, okay. We also have our full constraining workflow, so we can apply any kind of constraint to these lines as we want. We also have the ability to dimension and drive some of these sketches with sketch geometry. So here's a good way we can go through and see that this part isn't exactly perfect, right? These two sides are not perpendicular, or sorry, are not parallel. So we can go through and apply a parallel constraint, and then we can dimension these as a sketch object very easily. So as we're going through in modeling, we need to make a call whether we want to have a perfect CAD-driven dimension or if we want to extract the CAD dimensions as they are in the part. So come out of here and exit our sketch. We can see on our left-hand side, now we have a sketch object. And if we open this up, we can see that it's a dependent on this top plane and the gas valve. So we can turn our object back on here. We can see that our 2D sketch intersects perfectly with the bottom part of this skirt. And now what we're going to do is we want to make this solid geometry. So we're going to come up here to our Extrude tool. Now we're going to pick on our sketch here. And we can see the preview of the solid that's going to be created. So I have this offset value, a little bit over 2 inches, and I have my value here in my dialog. I can come in here and drag this to about where I think it should be. And as I'm getting close, what the software is doing is it's highlighting some of these regions red and indicating that the extrusion may need to stop here. The software is going through and identifying flat planes along the direction of this extrusion and snapping my cursor to that value. So this is telling me that the depth of this extrusion should be right around 1.18 inches, but the part is slightly more than that. So what I can do is I can come in here, and after fitting the extrusion depth to this value, I can come in here and actually override this to a CAD-driven dimension that's a little bit more round, which we can kind of anticipate is going to be the depth of this extrusion. So we can come in here and say check mark, and I'll hide my scan here. We can see now that we have a CAD shape. We have a couple of features here that make up this part, and we know they intersect and overlap directly with our scan object. We have a accuracy analyzer checking tool here that we can see how well we did. So I can turn this on at the top. And this gives me a color map of how well I've modeled the part. So green is within tolerance. Right now we're modeling at about 4 thou tolerance. So the CAD object is within 4 thousandths of my scan object. Blue means we're a little bit under. This means we have more scan information here. Red means we have a little bit more than our scan says should be there. And this is a good way for me to check to see how well I'm doing. So this is another indication that the bottom of this valve is a little bit worn, and this might be why we're modeling this part. This tool is also useful for when we are missing big features, so we can see in the middle, it's nice and red. That means we don't have a feature here because we're missing that hole. Or there might be some draft or other indication that we've missed a modeling feature that might not be evident when we just look at the part. So we're going to go ahead and look at some of the more automatic tools that are in Design X to start extracting some of this information. And these are the wizard tools. So the wizard tools goes through the manual process for us, and it creates these geometries that we can go back and edit a little bit later for a fully modeled part. So I'm going to come in here and go to my extrusion wizard. And then I can see we have a couple boxes that we need to fill in our dialog. So using the regions that have been applied to the part, I'm going to go through and select the profile of this extrusion. So if I'm looking at the end of this valve, I can see that this is just a nice extruded shape, and I'm just going to click on the sides of it as the profile of this extrusion. Then I come up here to my top, which is going to be where it starts, and then I can leave my bottom open, or I can choose where I want this to be finished. So I'm going to come in here and choose this flat plane on the back side. I also have this option for custom extrusion direction, and I can extract draft. So here I can choose a plane or other vector that I can force my extrusion to be propagated along. So I'm going to go ahead and go to the next step. We can see that we have a preview of the shape that was extracted. So we have the part of the valve that I wanted to extract, but I also have a little bit more material here than I originally intended. This is because the part itself is a little bit different than a straight extrusion because it's been used. There might be some additional bumps here, and the software is just extracting whatever we told the software to look at. So choosing those regions that I did, I have the geometry I'm looking for and a little bit of extra geometry. But this is good. I can use this to go and model my part. So I'm going to come up here and say check mark. And now this creates all the geometry that I wanted. So I have a plane, I have a sketch, and I have an extrusion. And since I have all this stuff, I can now go back and edit it and change what I actually want. So I can come in here into my 2D sketch. I can hide my scan information and look normal to my sketch. And I'm just going to remove this sketch shape on the right-hand side. Now we're going to come out, and now we're going to update our sketch. And since we have a parametric model here, the extrusion repropagates with the exact geometry that I'm looking for, sorry. So using these tools, we can repeat these steps and model the full part. So I'm going to jump to a finished model real quick. We're going to jump to a finished model real quick and show how we can get this geometry into a CAD package. So we have a finished model here. We have the full history tree of the part, and we want to get this out. So we're going to go into our Home tab at the top, and we're going to look at the Live Transfer section of the menu. So we have a number of different CAD packages here, and what this means is that we can send our history tree and everything that we've done into that CAD package. So you do need the CAD package on the computer, so I have a couple, but we'll start with SolidWorks. So I can click on SolidWorks. I have a couple options here, but usually we're going to start the first feature and send everything over. So I'm going to go ahead and say check mark here. And what this is going to do is going to launch SolidWorks, so it's going to just start a new part for us, and then it's going to start populating all these features one by one. It's going to send all the sketch geometry over, so it's going to get all that dimensioned information, and then it's also going to go send any of the reference geometry over into my part as well. So I have all my features and my sketch geometry in SolidWorks as if I had drawn them there without having to do any additional work. So here we go. Right now we're using SolidWorks 2017. Sorry, SolidWorks 2018. You can use any version of SolidWorks that you like, and we can just go right into it. So we're going to start here at the top and send everything over one by one and build the entire history tree of the part. We have the option to model certain parts of our model and send just those things over. So if we're making assembly of parts and we just need some mating features, we can use the modeling tools into Design X to accurately extract those informations and send them right into SolidWorks so we can model just the information that we need. So as we're going through and modeling the part, we can make a call for what we need. So when we're finished here, we have this export succeeded option. I'll just say OK here. And I have the full parametric model of my part. So I'm going to come in here and hide some of this geometry, and we can kind of see that this is all we have. So I'm going to come in here and look at my first model here, right click and edit. I can see that I have all my sketch geometry, I have my dimensions, and I have a symmetry line down the center here, and I could change this if I wanted to. So now I can treat this as if I had modeled my part here, and it has everything I need to go further. All right, so now we're going to hop back to our PowerPoint, and then we're going to walk through the ideal surface modeling workflow. So back here in Design X, we have a slightly different model. We have a model of a boat cleat, and it's pretty freeform, and it's been casted, so we know it isn't a perfectly nice sharp CAD model here. We might not be wanting to go to that. We might want to be going to more of a simulation type workflow, or we need to do some sort of analysis on this part, where we need the exact surface shapes as we scan them in a CAD environment. We're not interested in resizing any holes or anything else like that. We just need this information to go somewhere else. We can treat it as a CAD object when we're done, and that's exactly what we're looking for. So Design X has the full parametric tools that we looked at before, but we also have a surfacing workflow that we can go through to model this part a little bit quicker into something that's a little bit more usable. So here at the top, we have our surfacing tool set. And before we go into the tools here, we do need to do the same process of cleaning up the part. So we scan the top and the bottom of this part, we stitch them together, and we cleaned up some of the triangles. So all that has been done in Design X here. We have our polygons and our alignment tabs that we can go through that workflow and getting to this step. Now that we're here, we're going to go right into the surfacing tools. And today we're going to talk about auto surface, and I'm going to talk about all the manual tools that go into the auto surface tool set. So here, I'm going to go ahead and just click auto surface. I have a couple options here. All these options define manual parameters that we can edit and change in the manual surfacing workflow. So with mechanical, we're anticipating a little bit sharper corners and a little bit more prismatic shapes, whereas organic, we can kind of encounter anything under the sun. So this could be a very highly detailed art sculpture, or maybe we have a CT scan of an object that we need to surface into a CAD object like a vein or a kidney. Nothing there is either prismatic or anything has a corner in those types of models. We can choose to estimate a patch count, so the n number of faces that are going to be on our model. We can do a little bit of changing these options here, but there is a lower limit on number of surfaces that we're allowing you to fit to the surface because we still want to capture the information very accurately. The fitting method at the bottom has to do with the number of sample points and UV directions that we put on each CAD surface. So for some simulation tools, we're going to want to use the constant option, whereas adaptive will produce a little bit more lightweight surfaces, so it'll be a little bit easier to manipulate and edit in our CAD package. We just have a slider here at the bottom that will change our surface capture accuracy as well, which also has to do with the size of the file. The higher the accuracy, the more sample points we place on our surfaces, but that's just going to lead to a larger file. So we'll go ahead and go to the next step, and we'll talk about what the software is doing here. So in this first setup step here, we're going to go through two of the manual workflows, or manual surfacing workflow steps. The first is going to be the extract contours step, and the second is going to be the patch network construction. So those two steps generate a 3D spline network over the surface of the part. The contour curves, or the contour splines that we make, are going to be placed on areas of high curvature. So this means either corners or creases on the model. And it's going to separate those out so we really capture that information. The second thing that contours are going to go through is break up larger areas of the model. So if we look at this part, we can see that we'll probably get a contour along the top edge of this model, and then we'll get some across the surface of this part to further break up these larger areas. So these contours are acting as loops that we can further look at the surface of the model in a smaller area so we can handle that a little bit quicker and easier. The next step is the patch network, and that's going to be what we're going to fill in the rest of the shapes with. So we have all these green lines, as you can see, and these are all four-sided shapes. So these shapes are going to be what we're going to use to actually fit all of our sample points to the model. Now these patches are enclosed by a contour loop. So this is what we're going to use to segment the surface of the model. So in this second step of the auto surfacing workflow, we have the option to deform, which means we can adjust these edges and these spline nodes, and we can also set a sharp edge. So what this means is the end surface that we're going to make, or end solid that we're going to make, they're going to be made up of a number of faces. So the inside of each of these patches is going to be the face, and then the edge, or this spline here, is going to turn into a edge. So we're displaying this information as a spline, and the spline itself can exist off the surface of the mesh, where the spline nodes are vacuumed to the surface of the mesh. Underneath, the software is treating this entire line as vacuum to the surface of the mesh. So we're making these adjustments. The display may be different than what's actually happening underneath. The other thing here is we can set our sharp edges. And this is important because what we're making here are NURB surfaces. This means that their edges are tangently continuous, so they cannot actually define a sharp edge by default. So what we can do here is we can choose corners and other areas of the mesh to be sharp and break that tangent continuous constraint on our surfaces. So again, we can change our fitting method and our fitting options here, but we're going to go ahead and say check mark. So the next thing that the software is going to do is it's going to look at each one of these individual squares and fit a surface patch to it. So we go through is fit a U and a V direction along all these patches. This is why they need to be a square patch. We're going to sample them along the one direction, and they're going to sample on the other direction, and this makes a fishnet pattern on the surface. We call this a grid network. Now these are going to be the actual sample points and the sampling method that's used to fit the surface itself. And then we're going to stitch the edges of the faces all together in that tangent continuous method. Unless we had specified a sharp edge, this is what's going to happen. So if we scroll out here and we'll hide our scan object, we can see that we now have a gray object, and all those patch network and those patch lines turn to edges here, so we have black lines. And now we have an object that accurately represents the surface of the scan. So we can see all the casting defects and the casting surface texture. And we also have this label here at the bottom that we can easily make out from the model. So using this really quick method, we can get the model out as a CAD file format. And now we can treat it as if it was just an imported step or other solid file format. So I can come in here and make a sketch, and I can just cut a little bit of the edge of this off. So I can come here and make a rectangle, and then use a cut extrude, and I can treat this as a solid object now in either Design X or my CAD package to make an additional mating part, or simulate, or do any other regular CAD operation I would do to it. All right, so we're gonna hop back to our PowerPoint. And that was a quick overview of the feature-based modeling tools in Design X, and as well as the ideal surfacing workflow in Design X. Later in the series, we're going to touch on a couple other topics, and I hope you join me. All right, have a good day. Bye-bye.